Cool. So I was promising last time that we will find a way to write this a little bit more efficiently in terms of operations that involve the number 2. There was a discussion last time, and I think this I. So the number of bits here is 65, so I think this I needs to be 63 maybe. Okay, so this works pretty much by luck. And there would be a chance to not work because you see, if I is equal to 64, then we are overwriting the last \0 right here. Okay, and then what I guess it's happening is that the way the string is being laid out in memory, just by luck, right, there's another 0 coming at the end right after this array of characters, which is our string, right, just by luck. And because of that, our program works, but it's nevertheless an error. So we should start from I equals 63, go backwards, and fill up the array, right? Somebody asked last time, I think it was Catherine, how do we shift the bits? What if we don't want the spaces to appear at the beginning, right? If you remember, we have these spaces here, right? So how do we do that? Expecting a certain operation like in Python, we take the numbers from a certain index on, and that would automatically take a substring, right? So we don't have such operations in C. C is very low level, and one important thing to understand is that every operation that we do has finite time. There's no operation that takes an amount of time that would be dependent on the data that it operates on, right? Everything here translates into a finite sequence of machine instructions, each of which takes constant time. Okay, but there is a trick that we're going to use later, right? How do we avoid printing these spaces? We can't avoid having them, right? But how do I avoid printing them? Well, if I can take the last value of I here, you see, for the time being, sorry, here. If I take the last value of I, right, as I goes down, right, and I manage to return it out of the function, which currently we could because we're not returning anything, right? We could use that value to offset the bits here, and I'm going to demonstrate that. All right, why that works, we're going to understand later. So I'm going to go here and say return I, and this is going to be int now. Okay, so now what does this function do? Well, it fills the digits and returns, what is I here? Let me actually put I plus 1. What is I plus 1 here? Louder, please. The last field slot. Going backwards, right? When you say last, is going from right to left, right? So since we're typically going from left to right, it's the first non-space character, right? We could say it like that. But yeah, so exactly. So if I return that, I would know the start position inside the string of the position of the first digit, right? And I'm going to do the same here. Return I plus 1. I plus 1. So now, and this again has to become an int. Okay, so now I'm going to say here int first digit equals, and then I'm going to say digits plus first digit. Is this correct? Do I need I plus 1 or just I? I think first digit is good. And then I'm going to go here and say int first bit. And actually it should be like this, all right? I'm not sure whether you are aware of the debate between naming styles in various programming languages, right? So this one that you see here is called snake case, and then what you've seen before is called camel case, because every capital looks like a hump of the camel, right? And there's a big debate in the world on which language should use which style. C generally goes with snake case, right? Whereas Java goes with camel case. All right, so now we're expecting to not see the spaces anymore. The question is, what does this mean? What do you think it means? So first of all, what allows me, you see, this is an array, right? What allows me to just say digits here? We're saying, I mean, we're sort of saying this is very similar to Python. It's very different from Python, but it looks similar to Python, so it's something that doesn't strike you probably, right? Because it looks like we're passing in the entire array, right? Actually, we're not passing in the entire array, right? We're passing in the address of the array. Okay, so there is an implicit conversion that happens when I use the name of an array as a value. Actually, we never use the array. It automatically gets converted to its own address. All right. Now, if I take this address and I add this many locations, I'm going to get the address of the first non-space character. Right. So this will work fine. Okay. When we talk about pointers, we're going to understand that better. Let me just show you that it works so that you're not left with the impression that this is a completely useless language. Right? We can actually do interesting stuff in it. Well, and let's take all this. All right, and now you see that the spaces are not there anymore, right? Now, we have an explicit address operand. So you see, if I say digits first digit, this will be the actual first non-space character. If I write it like this, it should be very obvious that this is the, as a value, this is the first non-space character, right? The first non-space, the first digit, right? So I have a way of extracting the address of this, which is the ampersand. So this perhaps would be a lot, somewhat easier to understand, right? So we're taking the first non-space character and we're taking its address. This emphasizes the fact that printf actually doesn't take an array as an argument. It takes an address. All right, it takes a reference. Are you aware with the concept of reference in Python when you talked about objects and the fact that you would pass them into functions, that those objects are passed by reference? Yes? Okay, we're going to talk more about it. So this would be another way to do the very same thing, and probably a more readable way. Okay. The next thing we'd like to do, right? Same thing. And we're going to talk a lot more about this thing later. The next thing we like to do is understand the distinction between, understand these binary operations. And I'm going to introduce a bunch of binary operations. And let's introduce those by example, right? So I'm going to, now I'm going to input two integers, right? So I'm going to say first bit of first number here, first argument, and it's going to be this, and then I'm going to take this and use it here. And then we're going to say the first bit of the second argument. All right, and we're going to take the second argument here and the number 2. And I want to see the effect of the bits of the input number of the first arg. Let's say R and I am going to align them, make sure that they are aligned, because we want to compare them bit by bit. So I want to introduce the operations of conjunction, disjunction, negation, and exclusive disjunction, right? Exclusive OR. So let's do the following. Print, so int first, and you know what, I'm just going to say int k equals, and fill bits of, and okay, another thing we should be doing so that we don't keep calling a to l should be int a equals a to l argv1, right? And b is b equals a to l argv2. Okay, and then here we should have a, and then here we should have a, and then here we should have b. So int k equals fill. So now we have a problem, right? Because we're reusing the buffer. Okay? So we should clean the buffer before. You see, this entire space that we have here, we're filling it up with stuff, right? When we are reusing it, right? So we're using it for the first time here. When we are reusing it here, we should clean it up, right? So let's add up a cleaning operation, which would be for int j equals 0, j less than 64, j plus plus. We're going to do bits j equals, and what should I put here? You look at this, right? So what should I put here? Louder. Space. Very good. All right. So this is how we clean up. We restore it to what it was originally. Right? We start with spaces. So every time before using that buffer, we restore it to contain only space. Right? Obviously, we still want to keep the \0 at the end, but that \0 was originally there, and will be kept there by any operation we do, so no need to overwrite that. Okay, so in K now is going to be filled bits, and let's say we do A and B. So notice that there's a single ampersand, all right, which means bitwise conjunction. And then we do print F of A and B are. And then I'm going to align this, so we can see them one by one. Percent S backslash N. And we have to just do here address of bits of K. And let's see what this gives us. So now we have to input two numbers. Okay, hopefully it's not too large. All right, and let's see the relationship between them, right? So let's look vertically. You see the first digit, the first bit is 1 in the first number and 1 in the second number, so we get a 1 here, right? And that happens for the next 5 bits or so. Here we have a 0 and a 1, so the result is 0, right? We have a 0 because the arguments to the operation are 0 this bit and 1 this bit. So every time we have at least one 0, the result is going to be 0, right? If we have all zeros, like here, oops, so this is a 0, this is a 0, the result is 0. So this is the result of a conjunction. Okay? This is the bitwise operation. All right? Now, one very interesting thing with bitwise operations is that I can get any bit on any position if I want to, right? So for instance, I want to get the last bit of the first number. Well, I can just make the second number 1, right? So if I do that, right? Oh, and unfortunately, you see, this is where spaces were good. Spaces would have been good now. So let's remove the spaces. So let's stick with bits here. And bits here. Why do we do that? Because we want them to be aligned, right? And then bits here. Right? So notice that the result is 1, telling me that the last bit of this number, which is the same as this number, right, are 1. Not quite sure why the number is truncated. Did we do anything with... We only use fill digits once. Is there any relationship between this guy and this guy? No. What exactly did we change between this and this? Let's fill digits A. Is this number too small? No, but it worked, right? If I say digits here, sorry, we have to fix the bug first. Is it related to the fact that we have 2 arguments, no? Getting implementation fault immediately. Equals, oh, yes. All right. So another interesting one, right? Okay, so what happened? Let's explain what happened. So as we bump into these cases, we want to understand all the dangers of C. I think this is probably the most important thing. Okay, so what's the value returned at this A to L? We've seen it at work, right, previously, and it was working fine on 64 bits, right? So it's a 64-bit value. It's a long. This kind of value, right? Now, I'm declaring A to be int, which is only 32 bits. What do you think happens? Silently. With no warning whatsoever. Louder. The bits being cut off, right? So always when something bigger is trying to be moved into something smaller, the C will take the least significant bytes, the last 32, right? So if you think of 64 bits, the last 32 bits, right? The least significant bits, right? So if you think of the 64 bit of the long, right? Written from left to right, the least significant ones are the last 32. Only those 32 are put in the integer, right? And when we go here to perform the conversion, only 32 bits are converted and we get a smaller number, right? So, yeah, a very easy source of bugs. And the correct thing we should be writing here is long. All right, and this should make it work. All right, so the bits off, and what we want to do is see that whenever we use a 1 here, so notice now something very interesting, because we're using spaces before we go to the 1. You see, our procedure is very good. It notices the fact that this number would have been, this bit would have been a 0, right? But it's an insignificant 0 because it comes before the largest one, the largest one. There's no ones further from here, right? So there's no point in writing a 0 before a 1. Then because of that, that 1 is converted into a space. The same here. All these bits are not so long up to here. All these bits are zeros, right? But because they appear before the first one, they're converted into spaces. Is that clear? All right. So everything we said still stands, right? This one is conjoined. This one is conjoined. If I could just, this one is conjoined with a 0, which is what should be in the space, and produces a 0, right? Okay. So now if I conjoin a number with a 1, right? We conjoin it with a 1, and what we have here as a result is this last bit, and everything else becomes 0, right? So for instance, if I want to check whether a number is odd or even, I can just conjoin it with a 1, and if the answer is 0, then it's even. If the answer is 1, then it's odd, right? So you can try the same, conjoin with a 0, and then that's another thing that we should have taken into consideration. This is a 0, it's only spaces, so we should correct that actually. And this is another 0, right? Sorry, I did the wrong thing. Let's put an even number here, sorry, 2, 2, and put a 1 here. That's what I wanted to show, right? So I have an even number, I conjoin it with 1, and the fact that I have a 0 here on the last position means that this entire number is 0, and the original number was even. Okay? That makes sense? Cool. Let's do the next operation. All right? So let's do the shift. Okay? So I'm going to have int k equals fill bits of A shifted to the right by 1. Okay, and we're going to say the bits of A1 are, and we're going to say bits. All right, and let's see the result of this, and we also want to say printf the decimal value is %d \n, and here I'm just going to say A1, right? So we want to compare and have a first-hand comparison. Percent LD, I think, should be for printing long numbers, so we should do percent LD, so we get a warning. And did I reuse K? Yes, did I? So this K should not be declared. I can't remember what it is. Percent L, percent capital L. LLD, I think would be. Yeah, possible. Okay, LLD. All right, so let's go to, yeah, this, right? And look at the relationship between this. and this, right? And notice that we have a shift. All right, so this number is shorter than A, shorter than the first one. You can just see this, the X, there's a missing digit here, right? And then, but then if you look carefully, we have 1001 here, right? So the entire number is equal to this string of bits. Well, I don't know why this selection thing is trying to be smarter than me. All right, so the highlighted part is equal exactly to what you have on the last line, right? And now it's very difficult to count. It's a bit difficult to see that this, right? This is twice as large as this, right? That this number is half. The last result is half of the first one. But let's pick smaller numbers, right? So let's say here I have 1,000, and I'm just going to pick a bogus number here. It doesn't matter, right? And notice that the decimal value here is 500, right? So it's very clear here that this, come on man, you can do it. All right, this and this are identical, right? And then this halved is equal to this, right? So shifting by 1 means halving, dividing by 2, right? If I would do the reverse, all right? If I would do the reverse, I also need to compile. Right, notice that now by shifting in the opposite direction to the left, we get the double, right? The double value. And this is very similar to multiplying by 10 and dividing by 10, right? So if I take a number, BC minus L I'm going to do, and if I say 1, 2, 3 divided by 10, the result, does this work? No. Okay, let's do Python then, because Python can do integer arithmetic. Right, so if I do 1, 2, 3 divided by 10, you know that this is integer division in Python, right? I get 12, which is 1, 2, 3 shifted to the right by 1 position, right? And then if I say 1, 2, 3 divided, well, multiplied by 10, I'm going to say 1, 2, 3, 0, which is shifted to the left, and the new position is filled by 1, 0, right? So it's the same. If I'm in base 2, shifting to the left or right will be equivalent to multiplying and divided by whatever the base is, 2 in this case, right? If I'm in base 10, right, multiplying and divided by 10 means shifting to the left or right of those digits. All right, so this is what it is. This is the shift, okay? And at this point, we can actually go here and make this better, right? So instead of doing n%2, we can do what? We can do A. Conjugate? You mean conjunction? Okay, we conjoin with 1. Very good, right? So we saw that if we conjoin with 1, we get the last bit, which tells us whether it's odd or even, right? Odd or even is essentially the remainder of division by 2. So instead of saying n%2, we can say n%1. Instead of n divided by 2, we can say Very good. Shift to the right by 1. Okay, this should give us exactly the same result. All right. Now, with older compilers and architectures, CPU architectures, these would be significantly faster than addition and multiplication, right? It's actually no longer the case. First of all, the compilers are so smart, they will see that it's division by 2, or it's division by a power of 2. If I divide, for instance, by 4, I'm going to shift by 2 bits, right? Divide by 8, I'm going to shift by 3 bits, and so on, right? So the compiler is going to notice that, and it's going to turn it into an ampersand, into a conjunction and a shift immediately, right? So compilers are very smart nowadays. But even if they don't, the pipelined architecture inside of the CPU will still give you a actual execution time of this instruction of 1 cycle, even though it's multiplication or division, right? Which actually takes many cycles. Is this clear? We have a bunch of other operations that are interesting to explore. So let's introduce those. So I'm going to take the conjunction and put it at the end because it goes well with the others. It's closer to. I didn't do the right thing here. And then we have to put an int here. And we have to remove the int from here. And then let's keep adding other operations. So we have disjunction, bitwise disjunction, which is the bar. We have negation. Well, before negation, let's do exclusive OR. All right, and finally, we're going to have negation. So negation works only on 1 operand, not 2. And it's this operator, if I remember correctly. All right, so let's see what we get now. We're not using, we're not using this because we should write shift equals. All right. Oh. Sorry, I think I forgot which one is the bitwise negation. But it was itself. Oh, I think it is the correct one, but we're getting a negative number. All right, and because we're getting a negative number, we're starting from the assumption that all our numbers should be positive. So, what do you think the solution would be here? because we have talked about this as well at some point. Have we discussed unsigned last time? Have I mentioned the unsigned? All right. So now I'm giving away the solution, right? We can, instead of working with positive numbers, or with with full range numbers, negative and positive, right? We can work with only positive numbers. So I can add this in front, and then they don't have a sign anymore. So I wonder now if this would be ULLD. That would be, no, it won't. Oh, LLU. Yes, should be. Okay. So let's compile again. Let's run. Yes. All right. And again, it's a matter of how these numbers are. It's the same bits. It's 64 bits, right? What they represent is a matter of deciding, right? It's for us to decide what they represent and how we interpret those bits, right? So again, we have 64 bits that we read from the keyboard. All right, and now if you look at this, which is now an unsigned number, right, you're going to see that every bit is reversed, right? This is the negation compared to the first argument, which is here, right? So we have about 3 bits here, which are 0 because they're represented by spaces, and they appear as ones here. Okay. What do we mean by OR? The OR will be 1 whenever one of the arguments is 1. Is the complement of the conjunction of the AND, right? AND is 0 whenever one of the arguments is 0. And OR is 1 whenever one of the arguments is 1. Okay, so if you look carefully, for instance, here, right, we have a 0 and a 1. And if I go on this column, right here, I have a 1, meaning that 1 or 0 is 1. Okay, obviously 1 represents truth and 0 represents falsity. Okay. For exclusive OR, all right, how does the exclusive OR work? Right, so very good. Whenever they're the same, whenever the operands are the same, the result is 0. Whenever the operands are different, the result is 1. Right? If you think at a bit level, it's addition modulo 2 for 1 bit. Right? Because when I add 1 plus 1, I will get 1, 0, but I only can store 1 bit, so I'm going to store the last bit, which is 0. Right? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1, 0, but I can't keep the first 1. So therefore, the result will be 0. Okay? So that's the exclusive OR. So you can look at all these numbers and you can experiment with other numbers and make sure that the operation is correct. Now, there's other types of Boolean operators, the double ampersand and the double bar. What do they mean? So let's do this, and instead of fill bits of A ampersand B, I'm going to put a double ampersand here. What do you think we're going to get? Who bothers to predict? Who's trying to predict? Come on. What will it be? No one? We should have added another ampersand here. So, yeah, no one? The result is 1. Okay? Why is it 1? Very good. Okay, so C doesn't have Boolean values, true and false, right? Many languages do. Python doesn't either, right? And for a numeric value, or any kind of value, right? If the bits representing that value are all 0, that's false. All right. Any kind of entity you have that will be represented by some bits. If those bits are all 0, that's false. Whenever that entity is engaged in a Boolean operator, which is not a bitwise operator, a Boolean operator, right? That value is false. Anything else is true. So that's for input, right? That's for the operands. So whenever this has bits that are not all 0, this is true. If it has all the bits are 0, this is false. Same here, right? Now what's the result? Well, if the result should be false, it's going to be all bits 0, right? Which as an integer value is the value 0. If it is not false, if it is true, right, the bit combination will always be 1. Right? So it's very wide in terms of the input that it accepts. It accepts any kind of bit combination with all zeros being false and anything else being true. But in terms of output, it outputs 2 very specific values. 0 for false, which makes sense, it's consistent, and 1 for true, which is also consistent, but it doesn't return an arbitrary non-zero value. It returns exactly 1. Right? So this is how the specification works. It's a bit different from Python or JavaScript, right? Where if it's true, it returns the last value, right? The last value engaged in the expression, right? Yes. Anybody has used Node before? Right. So if I say A, B, C, and D, E, F. Right? The value is going to be DEF. So ABC is sort of non-falsy. It's truthy, as they call it. DEF is also truthy. It will return the last value engaged in, right? But in C, you will always get a 1. I think in Python as well. Let's see if we do the same in Python. So if I do A, B, C, I think 3 and 5. So first of all, we can only do it for integers. Oh, we don't have okay, here is and, right? And we get the last value as well. Okay, so yeah. So we don't have the ampersand. Python likes to be and okay. So we get the last value involved in that expression. If we use OR, what do you think we get here? Sorry, OR, and the same as in JavaScript. What do you think we get? Louder? So again, we're going to get the first one, right? As soon as I see a value that is is truthy, I'm going to just return that one, right? So it's going to return ABC. Okay, so that leads to a lot more creative use of the Boolean expressions. In C, that doesn't happen, right? So we're guaranteed to get either 0 or 1 as bit combinations, right? Think of them, right? So we get a bit combination that has all zeros for false. We get a bit combination whose last bit is 1. And everything else is 0 for true. All right, so similarly, right, for for OR. Right? So we get the value 1, which is the same. Let's put one of these values, let's make it 0. Right? So then here, this one will be 0 because of the conjunction. This one is still 1 because at least one of the sides of the operation is non-zero. Is right. And then the Boolean negation is, we've seen that already, is the exclamation mark. So I'm going to say not A here and not A. So again, it's a Boolean operation, so it's guaranteed to return either 0 or 1. So if I do this, I'm going to get a 0 because this this value is non-zero, right? The negation will be false, which is 0. And another thing we need to do is fix that bug that outputs only spaces when the number is 0. So I'm going to do that in a minute. All right, so let's make them both 0. That's what I wanted to do. And then you see that the negation of 0 is 1. All right. Whereas the bitwise negation of 0 is all 1s. Okay. Is everything clear now? How do we fix the bug where we have only spaces if the number is 0? So before returning I plus 1, what should we be doing? How do I know whether there's anything I need to do? Actually, not necessarily here. So if n is 0, okay, bits of 63 equals 0, right? Return 63, right? All right, so now, right, we have zeros whenever we need. We have some printout when the number is 0, right? We have a printout of 0 when the number is 0. And we should be doing the same, because if you look at this one, sorry, the digits, this one doesn't have any printout. So then we can do the same thing here, right? So we should say if n equals 0, bits of 19 equals 0, return 19. Okay. Now, obviously, we shouldn't have so many constants in the code, but we're not going to write. You're not going to write this kind of programs ever again. All right. These programs are just for your understanding. So I think it's okay as an experiment. Okay, because they just explain the structure of the number. Okay, so now we have. Oh, we still don't have anything. Did I save? Yeah. Good point. I also think I didn't save. Okay, so we have the 0 here. Cool. Questions? Yes.
About the bridge step.
Mm-hmm.
That's the negative numbers also, because they start with 1.
Very good question. Let's see what happens if we shift a negative number. All right, so I'm going to remove the unsigned. I'm going to remove the unsigned. That's a problem. That's a problem. Okay, let's forget about this program. Let's leave it as it is. All right. So let's start a new one. So we're going to shift the negative numbers, right? And I'm just going to pick this stuff from here. All right. I'm going to read a number which is going to be negative, and I'm going to say print f, and it doesn't have to be long. Let's just make it long. Long and int are the same, right? So I can just say int a to I, print f. Actually, let's say a shift it to the right by 1 percent d, and a shifted to the right by 1. And let's see what we get now. So the power of habit. And let's say -3. We should have done. So we're getting a -2, right? Okay. So let's try to explain. If I say -4, let me compile. So -4 here. I'm going to get -2, right? if I say, so I'm getting sort of the correct result, right? So let's try to explain this, what's going on. I'm just gonna, where's my explanation? My explanations are here. Let's just enlarge this. We can remove this, okay? So I'm going to take a number on 4 bits, all right? Which means that they range from -8 to 7 as integers, right? And on the number -5, how do we write that? So let's see, this is -1, all right? -2, -3, -4, -5, right? This will be -5. So this is the value 9 in if it were an unsigned number, plus 5. I'll get 14, which doesn't make sense. I should get sorry, I think it's this, right? Which is actually this is 11 plus 5 is 16. Yes. So this should be. So this is -5, right? So how do I know it's -5? Well, if it were an unsigned number, it would be 11, right? How do I know it's 11? Well, it's 8 plus 2 plus 1, right? So it's 11. And plus 5 would be 16. So 16 minus 11 is -5. So this is, if I use the complement of 2, this would be -5, right? So now I want to shift this number to the right. And then whenever I shift a complement of 2 number, which is not an unsigned, so this is a signed number, you would think that this bit gets filled with a 0, because that's what we saw when we were shifting to the left. But when you shift to the right, this bit stays the same. Instead of filling this bit with a 0, we keep it whatever it was. All right? So this is the rule of signed shifts. And then this number is going to be, let's see, it's 8 plus 4, 12, plus 1, 13. 16 minus 13 is 3. So this number represents -3. Does it make sense? So whenever I do a negative shift on -5, I'm going to get a -3. Okay? If I do that with, let's say, 6, right? 6 would be 16 minus 6 is 10, so this should be this number, right? So this represents 10. Why? 8 plus 2, which is 10, right? So actually it represents -6 as a signed number. And when I shift it, again, I do the same, right? I keep the first number the same, and I remove the last bit. And this is, as before, -3. Does it make sense? So when you type it as arbitrary bits, you should know the size in bits of your entity, right? So if you have a 32-bit entity, you only have a negative number if the first bit is 1, right? So if you wanted to expand this to 32 bits, this is -3, right? How do you expand it to 32 bits? Between the first one and the rest. Why not just put ones here? 28 ones. Right? So I'm going to take this first bit and I'm going to replicate it 28 times. That's how we expand. And this is, again, an interesting question, because let's try to convert A, right? So A is negative. All right? So now I can say int B equals, so not int B, let's say I say unsigned long B equals A. So let's see what we get out of this. Well, I should use colon because we used colon so far. All right. And let's say I have now long B equals, C equals A. So that's another thing we're learning. C percent, this should be LD, right? LLD. Percent LLD. And C here. And I forgot a backslash here. All right. Let's do another thing. Sorry. So B is unsigned long, so this should be LLU. All right. And this is long LLD, right? So all right. Sorry. Compile. Okay. So what do you think happens here? So the -3, we already know why. What do you think happens here? There's another one. We should have done it in the first place. Sorry. So I'm going to call it AA. Yes, int AA, because yeah. So it's going to be long AA equals A, and print F AA percent D backslash N, and we have AA percent LD. And then I'm going to still do another one, unsigned. But this should be not really unsigned, but percent LLU backslash N. And you're going to ask me, why should this be legal? Because we know that AA is not unsigned, right? But as you'll see, what we get is at most a warning. We might not even get a warning. We didn't get a warning, yeah. And now let's see what's going on, right? So let's look carefully at the program and see exactly what happened here. Okay, and by the way, these are problems that you would encounter in a lot of other places. I mean, you can encounter them in Java if you're not very careful, right? So Java doesn't have all this signed and unsigned, so this type of bug is less, it's not as easy to introduce. But in Java, you can manipulate bytes, right? So you can transform anything into a byte array, you can play with the bytes, you can assemble them back, right? And when you do that, if you're not aware of these things, you can very easily introduce exactly the same bugs. So awareness of this is generally important. This is a long number, right? And I'm assigning a 32-bit number to a 64-bit space. So up to this point, AA is an empty 64-bit space, right? We want to put something into it, but guess what? We only have 32 bits. We have the lower 32 bits. What happens with the upper 32 bits? Well, it happens, something very nice happens, right? As we were discussing here, we take the upper bit and we replicate it 32 times. and that will give us the same value in 64 bits, right? So there's no doubt that this is a 64-bit number, but it has the same value, which means that the upper 64 bits have been filled with the value of the first bit in the 32-bit number. Is this clear? Right? So this is pretty much what you want. If you think carefully of what should happen here, it's pretty much what you want. But now I take this AA, and I'm telling you, yes, you're giving me this 64 bits, but I want to look at them as if they were unsigned. I'm picking the encoding. You have the bits, but I'm picking the encoding that I want to use to display them. Does it make sense? Because you're going to say, oh, the correct thing to use here is D, because this is a signed number. And I'm telling you, well, I want to look at them as if they were unsigned. Nobody stops me, right? So this is in C, nobody stops. It's the same number, it's the same bits. The bits haven't changed from here to here. I'm looking at them as if they had a different encoding. And I'm getting this guy, right? Now, it would be interesting to understand what this number represents as compared to -5. Right? But interestingly, right, let's look at the next thing. So now I'm taking an empty space of 64 bits, but I'm saying this space's encoding should be unsigned. I'm going to put inside 32 bits that are signed. Right? Well, guess what? This is what matters. The unsigned here is what prevails. So it will take the 32 bits, right? It will put them in the lower 32 bits of the 64-bit entity, and it will fill up with 0 the rest of the 32 bits. Right? It will treat it as an unsigned entity. Remember that, again, this is C. So whenever we lay this out in memory, whenever a compiler does that, whenever the runtime actually does that, there's no way to know what's in there. So all the 64 bits will be filled with something specifically, right? So 32 bits will be copied from here, and then the rest of the 32 bits will be filled with something, right, to make sure that they're not random. Okay? But guess what now? If I want to print this as LLD, what do you think I'm going to get? I'm going to get -5, right? So I can play the same trick. I can say, oh yes, these are the bits of an unsigned number, but if I want to look at them as if they were signed, I can do that. Okay? Actually, it's very strange. I have no idea what's the relationship between this guy, and -5. Because if I do Python, all right, so if I do 232 -5, sorry, 132. I think I have to put brackets, which is exactly this number, right? And if I do 164 -5, oh, okay, I get this number, right? So this is correct. All right. All right, so there's more to explain here actually. There's more to explain. So let's understand exactly what happened. Scratch what I said before. Right? So we're taking yeah, no. So what I said about this guy is correct, right? So we're taking the AA and we're looking at it. So the value of AA is -5, right? But we're looking at it as if it were a unsigned number, right? Now, what happens here is very interesting. Okay, so this is a 64-bit entity, and we're saying this is a 64 unsigned. All right. So actually, I was saying that the unsigned prevails. Actually, the unsigned is ignored. So the size is what matters here, right? So it looks at this A, says, oh, this is only 64, 32 bits, but it's a signed number. So I'm going to expand it to 64. But I'm going to expand it to 64 as a signed number. So I'm going to fill up with ones all the extra 32 bits. And then I'm going to take those bits and copy them on top of this 64 bits, on top of this space, irrespective of the fact that this is unsigned. Okay? That's a very interesting thing. So I'm going to take the 32 bits and I'm going to see, oh, I need 64 bits. Oh, let me expand it. But because this thing I'm looking at is signed, I'm going to expand it as a signed number. And then I'm going to copy the bits into an unsigned entity as they are, and then from that point on, those bits are going to be regarded as unsigned. All right? Now, what happens here is very interesting. All right? So this is A. The first thing that happens is that we're going to look from this point on. This is what we call a cost. All right, we're going to be looking at the value here as being unsigned, but it's still 32 bits. And because it is unsigned, as I expand it to 64, I would fill the extra 32 bits with zeros. And then those 64 bits that I have obtained, I'm going to put them on top of C. All right, so how do I get this number? Well, as I expand as I convert from signed to unsigned, -5 becomes this guy, right? Why? Because you've seen the operation here, right? This is the value that we will obtain. -5 becomes, as an unsigned value, is the same bits. The bits don't change. Just the way we look at them changes, right? So the value becomes this. Remember Python, we're in Python now. Python is infinite precision, so we don't have these problems in Python. So then this is this value on 32 bits. As we expand it to 64 bits, whatever we're expanding an unsigned value, right? So we're filling up the extra 32 bits with zeros. All right. So this is now what gets printed here. It's a 64-bit value, right? But where the most significant 32 bits are zeros, right? So it has essentially what we see on the screen is the same thing. Does this make sense? Okay. So this kind of problems, it's the bread and butter of the C programmer, right? So these have to be mastered, and these are things that are encountered all the time. So you always have to think about how these bits go from here to there and how they are expanded, and where do you fill up ones and when do you fill up zeros, right? It's that's the daily life of a C programmer, right? You can imagine how much potential for bugs comes from this, right? And this is the reason why the ability to vary the amount of the number of bits for an integer type has disappeared from most languages, right? One, memory is not so it's very cheap now, so you don't care whether you're using 2 bytes or 4 bytes or 8 bytes for a number, right? You can always use 8 bytes. Its memory is cheap enough, right? And then there's no point in having to pay attention to this thing, to this nitty-gritty things. You want to concentrate on your solution or on your algorithm, and this takes away from that attention. Is this clear? Okay. So I'm going to want you to try to practice a little bit of this, right? This is not an essential part of programming as you go and grow and become professional programmers, unless you want to write operating systems and drivers, right? But it's good to be aware of them, right? You actually, every once in a while, you encounter this kind of problems in many other languages, and having this kind of understanding helps. At least knowing where to start looking for the problem helps. Cool. Thanks for coming. Sorry I was late. See you next time. If you have questions, feel free to stick around.